back early on, okay? A guy named Fisher discovered the active ingredients in coffee, tea, and caffeine and theobromine. Okay, he discovered the structure and synthesized them in a laboratory. Okay, in work that he carried out between 1882 and 1906, he demonstrated that adenine and guanine are part of the DNA molecules that make up your molecular structure. And this is way before Watson and Crick back in the 1950s. Okay, so 1882, 1906, adenine and guanine, along with some other compounds found in plants and animals, all belong to one family of compounds. He called these purines. Okay, this is one of the backbone molecules of DNA. Okay, all the purines have the same core structure and differ from one another by functional groups attached to the ring. Okay, this is a purine core structure. Different functions attached to this, but it's a 6-carbon ring. And instead of all carbons, there's 2 substitutions to that and a 5-carbon ring. Okay. That's the basic structure of your purine core, which is adenine and guanine. Purines are 2 essential components of the genetic molecules of DNA and RNA. DNA is a double helix. RNA is a single helix. Each strand of the helix is made up of a backbone of alternating sugar, which is ribose in RNA and deoxyribose in DNA, and a phosphoryl group. So you've got a sugar and a phosphoryl group that make up the backbone, then your purines attached. So you got this winding ladder and a corresponding sister molecule to it to make it a double helix. And of this ladder backbone, it's made up of a sugar molecule, phosphate, sugar molecule, and phosphate. And then the purine bases connect these strands together. Okay, so it's a sugar phosphate background. The sugar in RNA is ribose. The sugar in DNA is deoxyribose. That's the difference. So it's a sugar phosphate background. I'm sure some of these are going to get in the way of the next slide. Yeah, they are. Okay, so the purines are one of the 2 types of nitrogenous bases that project into the helix. Okay. Due to hydrogen bonding, the helix is held together and forms the structure of DNA. By reading the organization or the order, how they occur of these nitrogenous bases, you can decipher the genetic code of any organism. Okay. In 1884, he began his monumental work on sugars. So in 1890, he established the stereochemical nature of all sugars. And between 1891 and 1894, he worked out the stereochemical configuration of all the known sugars and predicted all the possible stereoisomers of those sugars. So stereochemistry is a study of the molecules that have 2 mirror image isomers. Now, that means they're not superimposable. Those are mirror images. It means that you can't take one another and lay it on top of the other one and superimpose it. It's like looking at your right and left hands. Your right and left hands are non-superimposable mirror images. They look the same. It's like looking in a mirror between the 2 hands, but you cannot position your hands in any way, shape, or form so that they're exactly on top of each other. Okay, that's what they mean by non-superimposable mirror images. Okay. Nature has selected only one of the 2 mirror image forms for common use in biological systems. So every molecule has these 2 images, but in nature, we only use one, or one will have one effect, one will have another, it's a totally different effect, which we found out in certain drugs. Fisher studied virtually all the sugars, but his greatest success was the synthesis of glucose, fructose, and mannose. All these 3 things are 6-carbon sugars. So we work with glucose, fructose, and mannose. Again, those are, each one of those 3 is a 6-carbon sugar. Basic chemistry through the looking glass. This is the children's story, Alice in Wonderland, Through the Looking Glass. Lewis Carroll's heroine, Alice, wonders whether the looking glass milk would be good to drink. So basically the story, it's not a kid's story. She falls through the looking glass and you have stereoisomers. So every isomer now is the mirror image of what it should be. That means it's not going to have an effect on the body or it's going to be poisonous to the body. Okay, so it's actually about a chemistry experiment is Alice in Wonderland. So many biological molecules like sugars exist as 2 stereoisomers. Okay, they're called anatomers. They're mere images that are non-superimposable of one another. Okay, because two mirror images form a curve, it's rather remarkable that in our bodies and most other body sugars, only one of the two is found. Okay, for instance, the common sugar members of the D family, okay, whereas all the common amino acids that make up the proteins are members of the L family. So all the sugars in our body are D, and all the amino acids are L's. Okay, D and L just refers to how the image rotates polarized light. Dextratory means it rotates it to the right side. Levitory means it rotates it to the left side when a polarized light is shined through it. It's going to hit it and rotate that light in a certain direction. That's all the D and L stand for. Okay, and that's determine the different isomers that you have. So the enzymes in our bodies that break down the sugars and proteins we eat are stereospecific. They recognize only one mirror image isomer. So all our enzymes only break down one of the mirror images. So if that other mirror images gets into our body, we either can't break it down and it's either going to develop into a poison or a toxin or something nasty, or just have no effect at all. Okay, so everything's designed by stereospecificity. Enzymes, everything works by their shape. Okay, and the shape is determined by the molecular structure of the compound. Okay, so knowing this, we can make an educated guess that looking glass milk could not be digested by our enzymes. Okay, because our enzymes only break down the one form, and the anatomy of the image, it wouldn't be digested. Therefore, we not get a good source of food for us. It could be a poison, it could be toxic, or it could have no effect at all. Okay, it is possible that it might be toxic to us. Okay, pharmaceutical chemists are becoming more and more concerned with the stereochemical purity of the drugs that we take. So you gotta remember that. 1960s, there's a drug called thalidomide. Okay, commonly prescribed in Europe as a sedative. This was used in pregnant women as an anti-nausea drug. And it worked great. It was fantastic. It relieved nausea. The only problem was the opposite form, the L form, because the D form of nausea, the L form caused severe birth defects. It caused thalidomide babies. Remember the Billy Joel song, "We Didn't Start the Fire"? Children with thalidomide is one of the lines in his song. Okay, these are children that were born without arms, basically. Their hands are attached to their shoulders. There's no upper or lower arms. Okay, that was one of the effects of thalidomide. Okay, so it's just because it's rotate the stereoisomer of the drug. And when drugs are made, you make both forms. It's just random which one it makes. So a lot of times it's a 50-50 mix it. Okay, and there's no way to separate them. It's very expensive and very difficult to separate. So you always just give both forms of the drug. And in this case, the one form worked really well, producing anti-nausea in pregnant women, and the other form causes severe birth defects. Okay. Now with thalidomide, they took it off the market in the 60s, and I thought the drug was gone. I had a patient come in my office probably 15 years ago now, and he was on thalidomide. And I told him that's impossible. You can't be on thalidomide. That drug was banned in the United States. And he was on thalidomide. So I had to look it back up. They re-released the drug. Now, it is a phenomenal drug for bone cancer, anti-nausea treatment for cancers like that for patients. It works great. Now, this guy he had bone cancer. He was 80, 85 years old. He's not going to get pregnant. I guarantee you. Okay. So we're not going to worry about having side effects as causing deformations in a fetus. So they do have the drug back on the market and is used in certain cases. But I was really surprised when he said the drug is back on the market. However, during the 100 years of women who took during that year, hundreds of women who took the thalidomide drug during pregnancy gave birth to babies with severe birth defects. Those are thalidomide babies. It turns out it was a mixture of two anatomers. One is a sedative, the other is a teratogen. Teratogen means a chemical that causes birth defects. That's what teratogen means. Okay, and these are referred to as thalidomide babies. They're no arms. Thalidomide is approved for use near the end of 1957. Okay, and it was pulled from the market in 1961, a year after the start. They noticed all those effects. It took 9 months for them to notice the effects for the babies to come to term. All right. There was over 10,000 cases of birth defects in that time frame, from 57 to 61. Okay. In 2006, the FDA reapproved the use of thalidomide. That took me by surprise, because I told my patient he couldn't be on thalidomide because I know that drug was pulled off the market, but they did put it back on. But because it is a good anti-drug, multiple myeloma, bone cancers, leprosy, okay, skin disease, certain skin diseases. Now, would you ever give thalidomide to a female of childbearing age? No, you pick a different drug. Okay, but it's a phenomenal drug for what it does. Okay. One of the common side effects of taking antihistamines for colds or allergies is drowsiness. Okay, remember, you take Benadryl, you get sleepy. This is a result of antihistamines are a mixture of anatomers. Okay, and remember, you're not going to separate. It's way too expensive to separate anatomers for drugs because they're the same chemical, the same composition. Okay, one of the anatomers, one causes drowsiness, the other is a decongestant. Again, so one of the side effects is drowsiness. The one is doing the good job as a decongestant, and the other anatomer is just causing you to be drowsy. Right? An acceptable effect. So one another compound of carvone is associated with the smell of spearmint. The other produces an aroma of caraway seeds or dill. So different smells can be from different isomers. One mirror image from limonene smell, like lemons. The other has an aroma of oranges. Ibuprofen is currently sold as a mixture of anatomers. So ibuprofen has two anatomers. Okay, one is much more effective than the other. One works really well, one just doesn't work as well. But why separate it? It just doesn't work well, but the other one's going to work just as well. So it's a mixture. Okay. Taste, smell, biological effects of the drugs in the body all depend on the stereochemical form. Everything works by shape, how it reacts to different receptors, what it's forming, what it looks like. Okay, and their interaction with cellular enzymes, what it binds to, or receptors, whether they bind receptors to cause an effect, or whether the enzymes act on those to break them down or cause another certain effect in the body. As a result, chemists are actively working on various methods of separating the isomers into pure form, which is not an easy task. There's no inexpensive way to do it. Alternatively, methods of conducting stereospecific synthesis that produce only one isomer is also being sought. If we can use this a procedure that only makes one isomer, that'd be just the same as isolating one. Okay, so we're going to do it by making the drug and then trying to separate it. They're working on methods for that, or just make only one of the isomers of the drug. Either way would be effective. By preparing pure sugar isomers, the biological activity of the compound can be much more carefully controlled. Definitely. This will lead to safer medications, less side effects, yes. So types of carbohydrates. Carbohydrates are synthesized by photosynthesis in plants. Okay. Plants take carbon dioxide and oxygen and produce glucose, carbohydrate, and water. No, hold on a second. I said that backwards. It produced so photosynthesis is carbon dioxide plus water comes to glucose, carbohydrate plus oxygen. I'm sorry, I think I said that backwards. So carbon dioxide and water are put together in a plant during photosynthesis to produce your carbohydrate and oxygen. So grains, cereals, bread, sugarcane. Okay, this includes the simplest sugars have the general form is CH2O and repeating unit. So you're going to have what the carbon, twice as many hydrogen. So if it's 6 carbon sugar, there's 6 carbon. You have twice as many hydrogen, H12, and the oxygen has the same number of carbons, those 6. So following this formula, you have C6H12O6 or C12H24O12. Okay, it's going to follow that formula. The carbon and oxygen is going to be the same. The hydrogen is going to be double the amount of the carbon. Right? That's their general formula. And they link together for storage in the body. And that's what the N is, that is repeating units. So N is an energy between 3 and 7. Okay, that's the number of carbon atoms you can have in the molecule. Just glucose happens to be one that is 6, which falls between 3 and 7. So glucose C6H12O6 is a major source of energy, and it follows that formula right there. So a gram of digested carbohydrate, 1 gram of digested carbohydrate gives about 4 kilocalories of energy. Complex carbohydrates are best for your diet, not your simple ones. The more complex, it takes more energy to break it down. The USDA recommends about 45 to 65% of your daily calories come from carbohydrates. So almost 2/3 of your intake must come from carbohydrates. A healthy diet should contain both complex carbohydrates like starches and cellulose and simple sugars like fructose and sucrose. However, the quantity of simple sugars, especially sucrose, should be minimized because large quantities of sucrose in the diet promote obesity and tooth decay, and also heart problems, type 2 diabetes, all kinds of stuff associated with it. Complex carbohydrates are better for us than the simple sugars. Starch that's found in rice, potatoes, bread, and cereal is an excellent energy source. Okay. Complex carbohydrates such as cellulose provide us with an important supply of also dietary fiber that you need in your diet also. So what is the current recommendation for the amount of carbohydrates that should be included in the diet? Of the daily intake of carbohydrates, what percent should be simple sugar? Okay. So 58%, roughly 60% of your diet should consist of carbohydrates. Okay, so 60, about 58% is about 60%. Less than 10% of your carbohydrate intake should be simple sugars. Right? Most should be complex carbohydrates. Okay, less than 10% simple sugar. Distinguish between simple and complex sugars. What are some sources of complex carbohydrates? Simple carbohydrates are monosaccharides. They're one unit. They consist of a single sugar unit. Glucose, fructose are examples. Okay. Complex carbohydrates are polysaccharides. More than one saccharide unit. They're links of different units together. Consists of multiple sugar units. Examples are starch, glycogen, and cellulose. Monosaccharides, let's talk about monosaccharides, simple sugars, glucose and fructose. Okay, one sugar, that's a saccharide molecule. Disaccharides. Disaccharides are sucrose and lactose. Those are 2 units that are put together, 2 sugar molecules that are tied together. Okay, so glucose and fructose are single monosaccharides. Disaccharides are sucrose and lactose, which are 2 sugar units put together. So 2 monosaccharides linked together. Linkage is called a glycosidic bond. That's what links 2 saccharides together, is a glycosidic bond. Okay. Oligosaccharides, okay, are 3 to 10 monosaccharides linked together by glycosidic bonds. And polysaccharides are a bunch, more than 10, a whole bunch. Starch, glycogen, cellulose. So you got monosaccharides, which is 1 unit. You got disaccharides, which is 2 units. Oligosaccharides, which is 3 to 9, 3 to 10, I'm sorry. 3 to 10 monosaccharide units linked together by this glycosidic bond. And polysaccharides could be thousands of them linked together. Anything greater than 10. Okay, so polysaccharides are these long chains of linked monosaccharide units. That's how we store sugar in our body. So monosaccharides are composed of carbon, hydrogen, and oxygen. Okay, basic formula we said was CH2N, where N is anything between 3 to 7. So many monosaccharides also contain chemical modifications, like amino groups, okay, phosphate groups. So naming the monosaccharides, okay, we got to name everything, right? We name on the basis of the functional group that is associated with the monosaccharide. If it's a ketone carbonyl group, we call it a ketose. If it's an aldehyde carbonyl group, we call it an aldose. Those are the two types of sugars. And we identify them as a ketose or an aldose. Okay, this is the Fisher projection of the sugar. At the top, we put the most oxidized end. Okay, so that's how we arrange these carbons. The most oxidized end goes on the top. Okay, and if you look at this, is this an aldehyde or a ketone functional group on the top? Who remembers?
Aldehyde.
Perfect. This is an aldehyde. So this is an aldose. Okay, it's 1, 2, 3, 4. 4 carbon sugar, and it's an aldose. Okay, aldehyde functional group. This one, most oxidized end at the top. Is this a ketose or an aldose? This one is a ketose, right? Because you got the R groups on both sides of the carbonyl group. So aldehyde function group, COOH, and a ketone function group, RC carbonyl group, and then R. All right. There's also a way of identifying sugars as a number of carbons in the main skeleton. 3 carbons is a triose. 4 carbons is a tetrose. 5 carbons is a pentose. 6 carbons is a hexose. Okay, those are all the same terminology we've been using before. Tri means 3, tetra means 4, pentose 5, hexo is 6. Okay, so we can tell now I got 2 ways to identify sugar. We list it as an aldehyde or a ketone by an aldose or a ketose, and we tell the number of carbons it has. Triose is 3, tetrose is 4, pentose is 5, hexose is 6. So combining both systems gives even more information. Number of carbon atoms and the functional group. Okay, so look at this thing. This is going to be how many carbon atoms in the back in the structure?
3 triose.
It's a triose. And is an aldehyde or ketone?
Aldehyde.
Aldehyde. So it's an aldose. Okay, so it's an aldose. We said it's a triose. So it's an aldotriose. Okay, that tells you the functional group on the most oxidized end, and it tells you how many carbons are in it. So aldose, aldotriose. And this, the actual name of it is D-glyceraldehyde. And we get the D because this functional group here is on the right side, the bottom one. And we're going to talk about chiral carbons and getting away from that before you actually determine all that. Okay, look at the next one. This next one is it an aldose or a ketose? Who wants to guess?
It's an aldose.
It's an aldose, perfect. It's an aldehyde there. And it has 1, 2, 3, 4, 5, 6 sugars. So it's a hexose. So it is a aldose and it's a hexose. So the name of this is an aldohexose. Okay. And this is going to be the sugar D-glucose. Again, the D refers to the property of where that OH group is on the last chiral carbon away from the most oxidized carbon. Which sounds like we'll get to how to determine that. Okay, aldose or ketose? That is a ketose. Our group's at both sides of it. And there is 1, 2, 3, 6 carbons. So it's a hexose. So it's a ketose, it's a hexose. So it is a ketohexose. Okay, and these names tell you what the sugar is. Ketoaldose means it's a ketone group. and it's 6 carbons. Means there's an aldehyde group and there's 6 carbons. Means there's an aldehyde group and there's 3 carbons. Okay. And this happens to be D-fructose. So in addition to 3 general names, each monosaccharide has a unique name too. Because the monosaccharides can exist in several different forms, several different isomeric forms, it's important to provide the complete name for these things we're talking about. So the complete name of the previous sugars are D-glyceraldehyde, D-glucose, and D-fructose. I should have to name those in just a second here too. These names tell us that the structure represents one particular sugar and also identifies this sugar as one of 2 possible isomeric forms, whether D or L. So what's the structural difference between an aldose and a ketose? What's the difference? Okay. An aldose has an aldehyde group at the top end. Has a ketose group at the end. So our group here and our group here, your carbonyl carbon. If one of these was a hydrogen, then it'd be an aldehyde. But that's an but it's a ketone, so it's ketose. So the one with the aldehyde function group called an aldose, one with the ketone group is called a ketose. Okay. So it's out of the way. So an aldose has an aldehyde function group at one end of the sugar molecule, and a ketose has a ketone group at the other end of the sugar molecule. Okay. So there's your aldehyde group right there. Okay, and it's 1, 2, 3, 4, 5, 6 carbons. So it's a hexose. So it's an aldohexose. Okay. And this one is a ketose. Okay. And this is a ketohexose sugar. Everybody see the difference between the aldehyde group and the ketone group? You can identify that on a test, right?
Yes.
All right, perfect. Explain the difference between a ketohexose and an aldohexose. All right. Look at this and we'll do an early evening here. Give you guys a break since you had your midterm on Tuesday. So let's do this problem here. So ketohexose and an aldohexose. Ketohexose. What does that mean? It tells you 2 things. It tells you there's a ketone at the top, and it tells you it is 6 carbons. An aldohexose tells you it's an aldehyde group at the top, and there's 6 carbons. Okay. So the ketose is a 6 carbon sugar that is a ketone functional group at the terminal end of the molecule. Okay. So an aldohexose is a 6 carbon sugar also, has an aldehyde functional group at the terminal molecule. So that's the difference between an aldohexose and a ketohexose. Now, what's the difference between a triose and a pentose? Who knows? Who wants to guess on that one?
A 3 carbon sugar versus a 5.
That's it. You got it. Couldn't have said it better myself. 3 carbon sugar versus a 5 carbon sugar. That's it. Triose is a 3 carbon sugar. Pentose is a 5 carbon sugar.